Hello and good evening to my GCC classes. Going to be taking a look at, continuing in Chapter 6, 6.4, looking at logarithmic functions. Now, probably at this point, the only thing we've seen about logarithmic functions were very briefly when we looked at our library of functions. And you might not remember anything about them at all. But there is a very close tie-in between logarithmic functions and exponential functions. A typical logarithmic function might look something like this. Y is f of x equals log base a of x. And I suppose I could have some number here or an exponent here. I could have some other constants here. But this is the typical type of logarithmic function. Now, if we think back to our library of functions, we know that there really are two different variations here. Just like with the exponential, where we had exponential growth and exponential decay, we can have logarithmic growth and logarithmic decay. If I have, for example, my parent functions, y is log base 2 of x, I'm going to have logarithmic growth. And the function is going to look like this. If I have log base 1/2 of x, I'm going to have logarithmic decay. And the function is going to look like this. So here we have logarithmic growth, logarithmic decay. Notice on the logarithmic growth, the function is increasing everywhere. Getting bigger and bigger and bigger through its entire domain. Logarithmic decay, notice that the function is decreasing everywhere. Notice that these functions, too, just like the exponential functions, are one-to-one functions. They pass the vertical line test, and they pass horizontal line test. These functions are both functions, and its inverse would be a function. These are one-to-one functions. Let's take a closer look at the domain and the range of these functions. Now, the domain, x values. I've got some restrictions here. Notice, this is my x-axis. It never gets to 0, and it's never less than 0. The domain is always going to be from 0 to infinity. You cannot take the log of a 0, and you cannot take the log of a negative number. The same restriction applies here. The x values get closer and closer and closer to 0, but they never get there. So the domain is going to be from 0 to infinity in interval form. Now the range, the y values, I can get anything you want here for the y values. The y values are negative, they're positive, and they're 0. So the y values can be all real numbers. Same thing over here. So the properties here, logarithmic growth, logarithmic decay, and it's really all about this growth factor here, this growth rate here. If it's bigger than 1, I'm going to have logarithmic growth. And if it's less than 1 but bigger than 0, I'm going to have logarithmic decay. Now, some of these things should be starting to sound similar to some of the properties and some of the things that we talked about in with exponential functions. And there's no accident in that. There is definitely a connection there, and we're going to see that a little bit later in this lesson. So where does a logarithmic equation come from, this whole big log-based thing? Well, if I have y equals log base a of x, that is equivalent to, I can rewrite this in exponential form as x equals a to the power of y. This exponential equation and this logarithmic equation are saying the same thing. For example, if I had something like 4 to the third power, 4 times 4 is 16, times 4 is 64, I could rewrite this equation is true, 4 to the third power of 64. I could rewrite it in logarithmic form as saying that 64 is equal to log base 4 of 3. Log base 4 of 3 is 64. 4 cubed is 64. So I can logarithmic version and an exponential version. Similarly, I could say something like log base 2 of 16 equals 4. What would that be in exponential form? That would be 2 to the 4th power is 16. So a logarithmic equation is just a way of rewriting the exponential equation. And we might be able to see why here. If I have my y value as an exponent and I want to solve this for y, I can solve this for y by rewriting it as a logarithm. Rewriting it as a logarithm. All right, so let's take a look at some more rewriting. So what I'd like to do now is get ready to hit pause on this, because I'm going to give you a logarithmic equation, and I want you to rewrite it as an exponential. So the logarithmic equation, suppose I have log base x of 4 equals 5. What would that be as an exponential equation? Well, this would be the base of x to the 5th power equals 4. All right, so now let's do it the other way around. Suppose I tell you that that 7 to the x power is equal to 2. Rewrite that as a logarithm. That would be log base of 7, log base 7 of 2 is x. So rewriting them between logarithmic form and exponential form is one of the keys of solving and working with logarithmic equations. A big part of the exercises out of the back are just in rewriting these things, changing from a logarithmic statement to an exponential statement, or changing from an exponential statement to a logarithmic statement. All right, so let's talk about, we're going to use that to help us to find certain values. So for example, if I want to find what is log base 3 of 27. Yes, we could do this on the calculator, but I don't want to do it without the calculator. And here's the way I'm going to do it. So I'm going to set it equal to x. Log base 3 of 27 equals x, and then I'm going to solve for x. I'm going to solve for x by rewriting it 3 to the power of x equals 27. 3 to what power is 27? Well, 27 is 3 cubed. Therefore, x equals 3. Log base 3 of 27 is 3. Let me give you one to try. How about find the log base 2 of 1/16. All right, I'm going to set it equal to x. Log base 2 of 1/16 equals x, and then I'm going to rewrite it. And as I rewrite it, I'm going to get 2 to the power of x equals 1/16, and solve for x. Well, 16, I know, is 2 to the 4th. 2 times 2 times 2 times 2 is 16. This is not quite right, though. I can't set it equal to each other. I'm going to use negative exponent rule and say 1 over 2 to the positive 4 is the same thing as 2 to the negative 4th power. 2 to the negative 4th is 1 over 2 to the positive 4. And then I'm going to get x is equal to negative 4. So this equals negative 4. The key, again, is in rewriting. to solve these things. Now, will it always be able to rewrite them nicely and easily so they've got the same base? No. We'll have some weird things, like if this was 2 to the x equals 1 over 15, I can't use that trick. I have to do something completely different. And we'll see that. We'll talk about that later and how to deal with those a little bit later. Let's see. We talked about did I talk about domain of logarithmic function? Let me see. It's in my notes already. I should have talked about it. But the domain of a logarithmic function, you can't take the log of 0 or negative number. So the domain is always going to be 0 to infinity, where the range can be anything. Let's take a closer look at domain. I know for domain, I know if I have y equals the log of x, just a nice plain old log, let's do, I don't know, log base 2 of x. Well, I can't take the log of 0, so the domain here is going to be from 0 to infinity. But what if it's something a little bit different? What about this one? Suppose I have f of x equals log base 6 of x plus 1. What's the domain of that? Well, again, I cannot take the log of 0 or anything negative. The stuff inside here, we call it the argument, the stuff inside here, that x plus 1, has to be greater than 0. Subtract 1 from both sides. X has to be greater than negative 1. There's your domain. So the domain is going to be from negative 1 to infinity, but not including negative 1. All right, how about this one? A little bit harder. G of x equals the log base 7 of x plus 1 over x minus 1. Oh gosh, this is a really tough one here. The first thing that occurs to me is I know I cannot have 1. If I have 1 here, then this is going to be undefined. It's over 0. If I have negative 1, 0 over anything is 0, so I can't have negative 1. I can't have negative 1, and I can't have positive 1. So right off the bat, I know that x cannot equal negative 1, and x cannot equal positive 1. It can't equal positive 1 because it would be undefined. I'd have 0 in the denominator. It can't equal negative 1 because negative 1 in the top would give me 0 over negative 2, which is 0, and you can't take the log of 0. So I can't have those values. Well, can I have values bigger than 1, like a 2? Well, 2 plus 1 is 3. Over 2 minus 1 is 2. I get a positive number. I can have numbers bigger than 1. Can I have numbers less than negative 1, like negative 2? Am I allowed to have negative 2? Negative 2 plus 1 would give me negative 1 in the top. Negative 2 minus 1 would give me a negative 3 in the bottom. Negative over negative is a positive. So I can have numbers bigger than 1, and I can have numbers less than negative 1. What about between? Like 0. Can I plug in 0? I can plug in 0 there. 0 plus 1 is 1. I can take the log of 1. I cannot plug in 0 there. Can I plug it in here? 0 plus 1 is 1. 0 minus 1 is negative 1. 1 over negative 1 is a negative number, so no, I can't. So the only values I'm allowed to have are the numbers that are less than negative 1, from negative infinity to negative 1, and the numbers that are bigger than 1. Those are the only numbers I'm allowed to have. That's my domain for this particular function. All right. Now, this is another point in the lesson where I would look around, see how people are doing with it. Do we need to do some more, talk more about domain? And I really don't care about range right now, but kind of talking more about domain, or are we ready to move on? Because I want to move on and take a closer look at the graph of log functions and the transformations. So, graphs and transformations. Oh, this black pen's about had it, hasn't it? So we know that if I have y equals f of x equals log base 2 of x, we should know what this graph looks like. This is one of the parent functions. Is it going to be logarithmic growth or logarithmic decay? The two values bigger than 1, I'm going to have logarithmic growth here. So this would look like something like that. Now let's mess with it. Let's do some transformations. Suppose I have f of x equals log base 2 of x minus 3 plus 5. What happened? Remember, with the transformations, they work exactly the same with the quadratics and with the exponentials, even the linears, moving things left and right and up and down. So here's my parent function. Now, what is this negative 3 doing here? Well, it's inside. This is going to be a horizontal translation of positive 3. So negative 3, it always goes the opposite way. So I'm starting here, and I'm going to move 1, 2, 3. So I'm starting here. There's my parent function, and I'm going to move 1, 2, 3. What's that plus 5 doing? Moving it up 5. 1, 2, 3, 4, 5. So I'm starting here, moving it right 3, 1, 2, 3, and up 5. 1, 2, 3, 4, 5. There it is. There's my new anchor point. So this point becomes that point. Here's my asymptote. Here's my new asymptote. And the function is going to look like this. The translations of right 3 and up 5. The new asymptote is the line x equals 3. Here it was x equals 0, but I moved everything over 3. So my new asymptote is the line x equals 3. Let's do another one with some more transformations going on in it. Let's consider, and I want to sketch a graph of the following function. F of x equals log base 2 of, let's make it negative log base 2 of x plus 3. All right, well, we know what the parent function looks like. The parent function, let's see, what happened to the parent function? I just dropped it over here somewhere. The parent function, the exponential growth, log base 2 of x, we know it looks like this. Well, what's this negative going to do? It's going to flip it upside down, and then the plus 3 is going to move it back 3. So here is my original function. Log base 2 of x looks something like this. But the negative is going to flip it upside down, and then the plus 3 is going to move it 3 that way. 1, 2, 3. So there's my asymptote. Move this point 1, 2, 3. And remember, it's been flipped upside down. So my new function is going to have the asymptote here. It was here. There was the asymptote. It's flipped upside down and moved that way. So my new function, flip it upside down and move it left 3. Flip it upside down, move it 1, 2, 3. Move it left 3. There's the new function. The domain of the original function was 0 to infinity. What's the domain of the new function? Well, I know if I can set x plus 3 greater than 0, so x has to be greater than negative 3 in interval form. I can write it like that. All right, so there is the function. Now, what if I wanted to find the inverse of this function? So there's the function, the graph, domain, and all that other kind of good stuff. Let's keep this same function again. And now I'm going to ask the question, find f to the negative 1 of x. Find the inverse of that function. Well, it's the same trick from before. I'm going to rewrite it start as an equation. Y equals negative log base 2 of x plus 3. Switch the x's and y's. X equals negative log base 2 of y plus 3. Now I need to solve for y. I need to get the y alone by itself. Well, how am I going to do that? First thing we'll do is going to get rid of the negative. Multiply both sides by -1. So now I've got negative x equals log base 2 of y plus 3. Now what? How do I get this y alone by itself? The key to getting this by itself is to rewrite. This is a logarithmic equation. I'm going to rewrite it in exponential form. In exponential form, it's going to be 2 to the power of negative x is equal to y plus 3. And now all of a sudden it becomes easy. Subtract 3 from both sides. 2 to the negative x plus 3 is y, and that is my inverse. There's the inverse. Here was the original function. Switch the x's and y's and solve. There is its inverse. Here was the original function, and there, switch the x's and y's, there is its inverse. And of course we could talk about the domain and range of the inverse. The domain and range of the inverse is the range and the domain of the function. The domain here was everything greater than -3. That would be the range here. The domain of this function is going to be, well, let's see, what's the domain of this function of the inverse? You can plug in anything you want in there for x. The domain here is all real numbers. That must mean that the range up here was all real numbers. All right, what else do we need to be able to do? Now, this is another one of those points where I would look around and, okay, how are people doing with that? Do we need to do another one where we're finding the inverse? Was one example enough? Let's talk about solving. Logarithmic equations. For example, if I have solve log base 3 of 4x minus 7 equals 2. How on earth would we solve this? We want to get x alone by itself. X equals something. Well, you might be able to guess, you might be able to see the key in solving these is going to be to rewrite it first. If I rewrite it in exponential form, I get 3 to the power of 2 equals 4x minus 7. And then all of a sudden this becomes easy. 3 squared is, 3 times 3 is 9 equals 4x minus 7. Add 7 to both sides. 16 equals 4x. Divide by 4, x equals 4. And there it is. The key again is in rewriting it. Let's do another one. So I'm going to put another one up here, and I'm going to pause. Go ahead and hit pause on the video and see if you can solve this one. How about log base x of 64 is 2? Hit pause and try it. All right, so if I rewrite, I get x to the power of 2 equals 64. What squared is 64? Take the square root of both sides, and I get x equals plus or minus 8 when I take the square root. Positive 8 squared is 64, but so is negative 8 squared is 64. So it seems like I've got two answers, a positive 8 and a negative 8. X could equal 8, x could equal negative 8. But remember where the x came from, the base of the log. I cannot have a negative base, so I only have the positive solution. With logarithms, we have two special bases. Oh, I don't want to use that black pen anymore. I think that one's dead. So we have base 10, log base 10. This base is called the common log. And sometimes we just write it as log without any base at all. If you see log in an equation or graph or something like that and there's no base there, then it's automatically base 10, the common log. Another common base is base e, that Euler's number. Here it comes again. Whenever we're dealing with logarithms and exponents, e is going to be all over the place. So log base e is called the natural log, and it's just written as ln. ln, log de natural, French. And we've seen that on the calculator. As a matter of fact, if we take a closer look at the buttons on the calculator, notice that I've got log here, which without any base, that's the common log, and I've got ln here, which is natural log, log base e. Now, on some calculators, they do have change of base formula, and we'll be talking about that as we really start getting into the properties of logarithms in the next lesson, 6.5. But I just want to take a moment to look at either common log or log base e and do at least one sample problem with common log or log base e. So let's say I want to solve the e to the 3x equals 2. Oh gosh, what on earth is this going on here? Well, this is an exponential equation, and my first thought is to rewrite both of them with the same base and then set the powers equal to each other. So how can I write 2 as e to some power? And of course I can't. There's no nice and easy way of doing that. But I can rewrite this. It's in exponential. I'm going to rewrite it in logarithmic form. In logarithmic form, it would be log base e of 2 is 3x. Log base e is natural log of 2 is 3x. The natural log of 2 is just some number. If I take out my calculator and I do natural log of 2 equals, there it is. It's just some number, 0.6931471806 approximately. Divide both sides by 3, and I get x equals the natural log of 2, which is some number, divided by 3. In other words, x equals, there's the natural log of 2, divided by 3 is approximately 0.231049, yada, 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 whatever that is. The exact solution would be natural log of 2 over 3. Natural log of 2 is some number. Do that on the calculator. Whatever you get, divide that by 3. All right, so we're not going to see any big word problems yet. There's some pretty good ones in this section that we might come back and look at after we've done all of our properties of logarithms and exponentials, and when we start applications, we might want to come back to 6.4 and look at some sample problems. But until then, I think we're done with 6.4. So what I'd like you to do now is to do the homework 6.4, which starts on page 454, and I want you to do problems numbers 9 through 55 odd. And what are you going to see there? Well, 9 is a concept question asking to complete a statement about natural logs. 11 through 17, you're changing from logarithmic to exponential form. 19 through 25, you're changing from logarithmic to exponential, just rewriting it. Problems 27 through 37 is you're going to solve the logs without a calculator by rewriting them. The key is always going to be rewriting them. In 39 through 49, just talking about finding the domain. So looking at the argument of the logarithm and making sure that it's always greater than 0. And then 51 through 55, you're going to use a calculator to evaluate some expressions using logarithms there. And be careful with the calculator. Weird things can happen on the calculator. Make sure you've got the parentheses in the right place and all that other good stuff going on. So that's 9 through 55. A lot of ones very similar to what we just did. And then I want you to do problems 71, 73, 77, 87 through 109 odd. 71, 73, and 77 are finding the inverses of logarithms. So the key with finding the inverses is to rewrite into an exponential equation. and then solve it for y. 87 through 109, just the odd numbers there, are solving. All of these will come out to be nice and well-behaved numbers as you rewrite them and then do them on a calculator, very similar to the ones we did. The key, again, is rewriting. I think you'll find that the key with many of these is rewriting them. So another kind of brief video here, only about half an hour long. Normally in class I would spend some more time. I've got more examples that I would do depending on the feedback that I would be getting from students. Oh, I didn't understand this, or I didn't understand that, and we could do more examples as needed. You've got the homework, look at them, go through them. The answers are in the back of the book. I haven't found any mistakes with the answers, but if there's anything that's weird, you're not sure about, shoot me an email on it and give me a chance to email you back or to post a solution and talk about it. A lot of times, look for posted solutions where I'm just going to post a picture where I'll do all the work, and then I'll just post it saying, oh, this is 6.4, number 73. A lot of people were asking about it. Here it is with all the work, and I'll just post the picture here. Once you're done with this assignment, I want you to email the assignment to me. That's robert.shannon@gccaz. Oops, I don't have room for the edu. And you can either scan it and send me a PDF file, which is the better for me, so I can print it off and then grade them. Or if you can't scan and do PDFs, just take a picture with your cell phone, and it'll come out as a JPEG, not as a GIF. Don't make it anything moving. Don't do GIFs, but JPEG, and then just email it to me. And you might have more than one page. You might have 3 JPEG images that you send to me. They shouldn't be so big that you can't email them. Don't take any videos. Don't take videos of the homework or anything like that. Sometimes those files get too big and I can't print them out. So with all the emails, I like to print them out so that I can grade them, and then I will enter grades. You've probably noticed that the gradebook has changed, and now your grade is going to be based on these assignments as you complete them. Any questions? Shoot me a question. Good luck, and I'll talk to you again soon. Bye.